I think, well, I should introduce myself. I'm Kiko Todo. I'm Director of Climate Repair at Anthropocene Institute. We spend all our time thinking about the things that we could do that could really make a difference to the climate crisis. Did I just say that word in 2026? Okay, well, just don't tell me. What could really make a difference, what could really move the needle in terms of cheaper energy, transformative technology for the climate and for the planet. And so we are here to think big, to dream big, to think the thoughts that are, well, ARPA hard, right? So before we get to the actual activity and the competitive brainstorm, what I'm going to ask you guys to do is listen to a bit of a discussion here. We have a very distinguished panel. We have Rachel Sleba, who used to be a program director at ARPA-E, is now VC, and DC is that. What is the difference between those?
What is the difference between what?
DC and VC.
Oh, DCVC used to stand for Data Collective Venture Capital, and now it stands for DCVC. So I'm a venture capitalist at the firm DCVC.
So let's start with you, Rachel. So when you think about the path towards really transformative technologies that could really make a difference in bringing substantially the cost of energy down in a reasonable period of time, what comes to mind first?
Yeah, I mean, well, so first, welcome. I'm delighted to have you all here. I actually was a student at the student lunch at the very first one ARPA-E ever had, so it's a distinguished tradition, and it's nice to see it still going. And now we have real programming and real conversations, which is even better. So 10x cheaper energy, that's a big challenge, right? Like 10% cheaper energy, you can sort of imagine that. It's even hard to imagine that while electricity prices are going in the opposite direction. But an entire order of magnitude in cost improvement, we have to really think differently about what are the resources that can be that much more efficient. So you have to have something that is incredibly energy dense, is incredibly resource efficient, and is manufacturable and scalable. And so that leads you into some directions, maybe fission, maybe fusion. You could imagine breakthroughs in technologies like maybe geothermal, possibly wind and solar. But I think you start really moving away from fossil fuel, where it's hard to imagine that getting cheaper and cheaper when it's a finite resource that is getting used up, and actually quite a bit of innovation has been done there. So that's kind of, it's like if you look a little bit from a first principles of what are even the directions you have to go in, what are the candidates, that's where I start.
Larry Forsley is a PI at NASA, where, Larry, I'm not going to butcher your field. Tell us what you do and tell us how you think about much cheaper energy.
Yeah, well, our big problem, so I want to thank all of you for showing up here in our august panel as well. I actually had the front door at the very first ARPA-E meeting at another Gaylord in Washington, D.C. 14, 15 years ago. The work that I do at NASA is solving our problem, which is, in a microcosm, the same problem we have on Earth. Batteries won't do it for us. We can't burn fossil fuels out in space. Everything is at a premium. Volume, mass, and we can't fix things. The minimum requirement is whatever we put up has got to have a lifetime of at least 5 years, ideally 10 years. We'd like to have a minimum of 10 to 100 kilowatts. A lot of our plans have us putting megawatts out in space, either surface power, which I work on, or for propulsion, which I also work on. So if you take all of the problems we've got at NASA, hey, solving it on Earth in 10 years and being able to cut it back seems like an easy problem. It's not. One of the things that I'm concerned about is even if we were able to get technology for space that gave us, let's just say, megawatts, what is the infrastructure required to build that? Where did the people come from to build these devices, to design these devices? And so there's a much larger scope than just having a way to get the energy, what does it do in terms of disrupting economies? And where do we get the people and the technology to put all of it together?
One of the great opportunities is that there's a lot of big energy consumers that are industrial, such as AI data centers, that want energy behind the meter, so they say, that don't need to use the grid because the grid doesn't have the energy available. That's creating a market for innovative, clean energy. And in my view, making energy 10 times cheaper is actually quite easy. Solar got 100 times cheaper in 40 years because they were allowed to innovate. Nuclear didn't change at all for 52 years because all innovation was stalemated by regulatory. If it had simply got 5% better every year, like a normal industry, it would now be 11 times cheaper. So all we have to do is unlock stuff we already knew we should have done 20 years ago.
I'm wondering which of two directions I should take this in. One is, what would the world look like if we had much cheaper energy? What becomes possible to do that we can't do now in that different world? Larry, you look like you're wondering about that.
Now, one of the things that becomes very important is if you really do have abundant energy, it changes the way you manufacture things. The processing of ore and all of these things, they tend to be both energy intensive and water intensive. If you can increase the energy, you can reduce the water. And that also goes, as far as desalination, things like that. So it makes a huge, huge difference.
Rachel.
Yeah, clearly the conversation today about energy expansion is related to compute. That's part of it, right? And so radically cheaper energy makes it easier to expand compute. That's a near-term goal. Absolutely production and manufacturing, but electrifying everything. But if you think already there are quite a number of people on Earth with restricted access to power, it's not just cheaper energy here, it's cheaper energy everywhere. And so here it's like, oh, okay, maybe I can have an EV with longer range, or I can charge it more effectively or whatever. But really it's transformative in countries that have very low electricity and energy deployments today, where now it's about refrigeration, it's about keeping medicines cold in hospitals, right? It's life-changing.
I know you have a lot of thoughts about this, Carl.
I could go on for hours about what we could do with cheaper energy, but one thing I'll point out is one of the biggest expenses to the US government is war. 90% of war since World War II has been fought over access to oil, funded entirely by oil revenues. If we decide that we can make oil or hydrocarbon fuels cheaper using nuclear energy, environmental carbon, and hydrogen from water, as we can, then we suddenly don't care where there's oil underground, and we need to find a different reason to fight wars.
Oh, can I amend my answer? Because I realized I didn't say the obvious one is we can fight climate change. Right, if we have lots more energy, we can do direct air capture, we can make synthetic fuels. Like the biggest existential solution really is having energy does help you fight climate change because it takes energy to solve a number of those problems.
Yeah, we burn things because separating carbon dioxide from combustible things is exothermic, so you need energy to put it back in. It seems relatively straightforward. That's how I also look at it, but I also think often in terms of development. Many developing countries, if you look at sub-Saharan Africa, the main block that they have in growing per capita GDP is just lack of access to energy. You still have people using biofuels and like charcoal and things like that just to cook. So if we had much cheaper energy, we'd probably have much less global poverty, right? I want to, yeah.
Else in here to consider. You talk about data centers, and there's a lot of discussion about putting small modular reactors at data centers. One of the concerns that is never brought up is 40% power budget of a data center is keeping it cool. Second thing is, when you put electricity into a data center, it eventually all shows up as heat. So So if you put a small modular reactor, or 2 or 3 or 4, with a gigawatt of electrical power, you're talking about 4 gigawatts on average, 3 to 4 gigawatts of thermal power, independent of what is being used in the data center. And the way we get rid of this is we typically use water and we produce steam into the air. Well, in California, we're talking about putting a data center out in the Imperial Valley. It is short of water, and someone thinks that we can drag solar panel electricity all the way to it. This is not a good solution, but the problem you run into with any of the typical ways of making power is you're limited by the Carnot cycle. At best, you get 30 to 40% efficiency conversion to electricity. You've got to do something with all that heat. And if you talk about building very small, let's say nuclear reactors you put in your iPhone, it's going to get rather warm.
Obviously, at Anthropocene, we're very focused on various types of nuclear energy, and I know that a major concern has to do with manufacturability. But I think it's not necessarily obvious to everyone why this is so important. So I wonder, Carl, if you could talk a little bit about why a manufacturable reactor is different.
Well, I don't think any of us know what manufacturing looks like today because we haven't had time for the AI-powered robots to take over making things. But, you know, one thing I do know is that robots are mostly made of energy. So if we make energy 10 times cheaper, robots get 9 times cheaper. You know, solar panels also get 9 times cheaper. If we start with energy in the supply chain, that's 10 times cheaper. So you actually don't put solar out of business just because you make nuclear energy 10 times cheaper. They go down together. And actually, if you want to bring energy costs down 10 times, you actually only need to bring energy costs down 3 times, and then make sure that you use the cheaper energy to manufacture the equipment for energy, and you've already got to 9x cheaper. So the supply chain here is key. It's a virtuous circle. But yeah, manufacturing, we already know how to make oil platforms and ships are built entirely by robots, just about. You know, there's only 7 hours worth of labor per ton of steel erected. So the best shipyards can make any energy system we can dream of.
So, do you want to have a...
Yeah, I mean, maybe that frame of how do you actually get something cheaper, designing for manufacturability is an idea that I think we have, but has been, to Carl's point, maybe a little bit lost in the United States, where many designers haven't actually built anything before, and we don't do that much manufacturing on shore, and we don't know the most efficient way to operate factories. And so if you're looking at how do you really scale something quickly, which helps save costs, how do you get to very large scale, which helps save costs? The integration of manufacturing from the beginning is really important. And I think that's a big message here at ARPA-E, where we have a lot of sort of early stage teams out of universities, laboratories, and it's not necessarily what they're thinking of first. So the science has to work. The ability to actually scale and efficiently and quickly and repeatably make something so that you can really deploy it is an integral piece that you have to consider sort of early on in your technology development.
Larry, do you have a thought on this?
And manufacturability is a very important thing for us, both at NASA and on the ground. Again, I'm very concerned. We may have enough robots, but who do we have to build the robots? Well, the answer to that is more robots to build the robots, but at some point, someone has to fix them, someone has to essentially design them. There is a virtuous cycle, but it's perhaps at this point self-limiting. And if we're talking about decreasing the energy cost by a factor of 10 in 10 years, we can't start 9 years from now. We got to start now. And a lot of what you folks are doing in school and things, that's really critical. Knowing subject matter deeply, being able to communicate, being able to have a path that you want to stick to. And even before you know what you really want to go into, at least you build the fundamentals. You get a path and you get all of the studies behind it. And you know things both in math, engineering, science and the arts, because then you're well-rounded and you're in a good place to push these things forward.
Yeah, I guess I have one more comment. That is, energy is cheap for, in some places, but it's not very well distributed. The United States had a rural electrification program that famously got nearly every US household, even on farms, electricity. But maybe it's time for that to end because it's cheaper for most rural houses to power themselves with solar, which is not very powerful, but beautifully distributed, at least in places that aren't always cloudy. We have an opportunity to make small-scale distributed nuclear energy that's safe enough to cover the places that, the grid doesn't. And Larry Forsley is an expert in that, among others, and so we need to be thinking about how we distribute energy more equitably. You see countries with abundances of oil that don't even supply electricity to their people. And
Larry, I think you're called on to go deeper.
Carl's called me out here. I happen to agree with this. You look around the country and you see these huge things that have various names like walkers and things. They're carrying the high voltage tension lines. You're losing maybe 5% of your power eating up the air through the tension lines. But there are places with data centers that are hungry for power, and now local towns, and I'm thinking in particular Texas and Loudoun County and Virginia, they don't want any more high tension lines. And so they're going to have data centers starving for power. Now that goes right back to saying, well, let's not have a distributed system with power being generated hundreds of miles away. Let's put the power local. And if you can build it small enough, and you can build it efficiently enough, then you can power a town. And you're disconnected from the grid. There was a study that was put out by ARPA-E, by Scott Sue, who started the fusion program within ARPA-E. And it was put out by the Jason. And if you read through it carefully, they note that fusion power systems, because of economy of scale, need to be on the order of 1 gigawatt electric. Your underdense plasmas inside. The problem is that runs counter to people wanting to have distributed power. So instead of having a few fusion plants across the country, you'd like to have fusion plants or power plants that are much more local. Just means you now have to deal with, as Carl was saying, regulatory issues, but there's also the issue of safety.
Let me pick up this point about regulation. There is I'm going to caricature this. This is a Mickey Mouse version of the argument, but there are people who go around and will tell you the entire problem is the NRC, maybe asterisk local NIMBYs. And that really, if we had a regulatory framework that allowed fast iteration, that was less hyper-conservative and less based on difficult to defend levels of linear no threshold and these very conservative frameworks for risk management, that we would have gotten to that 5% cheaper year on year over 2 generations that would have put nuclear at an unbeatable cost advantage to hydrocarbons now. Is this Mickey Mouse version just ridiculous, right?
The truth is somewhere in the middle. I think there certainly was a period where there was a strong backlash against nuclear, and that also coincided, maybe let's back up a second. So I'm a nuclear engineer by training. I used to be a nuclear engineering professor. So in the 70s, when we had oil shocks and we were building nuclear reactors here, reactors became very expensive. Interest rates went up. Reactors became intractably expensive to build. The United States was quite poor at building nuclear reactors. Every single one was its own project. We had a different vendor and a different utility and a different EPC firm. We never built the same thing twice. They kept getting more expensive. You add massive interest rates on top of that, nuclear industry dies. Then we have 3 Mile Island. That was a great nail in the coffin. So now we have a bunch of regulatory buildup. We have cost pressures against nuclear. There was just no driver to pull it forward. So on one hand, yes, regulation mattered, but there weren't economic drivers to solve that problem. Also after the oil shocks, right, so nuclear had become too expensive. We were very bad at building it. regulation built up as a reaction, but no one was really trying to build new nuclear power plants anyway because they were too expensive. And we actually, load stopped growing because of conservation as a result of the oil shocks. And so then in the early 2000s, we started getting interested in nuclear again because of climate change. And that's where you can start saying, actually, maybe there was a little bit of a regulatory barrier. We started to have some action moving things forward, but then fracking happened and natural gas became incredibly cheap. We still didn't have load growth. And so there was, again, no real economic driver to move forward on nuclear. And so now finally, we have massive load growth. There is an economic driver to move forward on nuclear, and we're finally starting to see some change in the regulatory framework.
Carl, can you?
Well, I'm sad that we love our AI more than our humans, because I think there always was economic drivers. California pretends like we have a shortage of water, but actually the Pacific Ocean's water level's rising, and we should be running the Colorado River backwards to send water to states that don't have an ocean. No reason not to, and California is so far behind the rest of the world in desalinization. There's no environmental penalty either if you have a rich enough energy budget that you don't have to cut corners and dump brine on sensitive sea life. So I think the problem, again, is socioeconomic. We have let utilities make decisions about what energy systems we buy, and they are really negative on making their product 10 times cheaper because they figure they'll get 10 times less money. But in reality, if you do that, I'm pretty sure people will buy 20 times more energy and they'll make twice as much money. And that's Jevons Paradox. But they're not going to bank on that.
I think this point about the incentives in the system and sort of the break, like there are all these fiefdoms that sort of keep things how they are, and people don't see how they're going to capture value, and there are all these structures in the way, these are a lot of the real challenges.
One of the best examples of what happens with this is early on when solar was starting to take off, utilities thought it was a great idea. And then somebody figured out after a few years that they were losing money because people were generating power at home and taking their excess power and putting it on the grid. In fact, I look at my bill. I live in California, about 20 minutes from here. I look at my bill. My bill is 2 to 3 times higher for getting the power to me than the power I buy. And it even goes further. There are disincentives in Utah and Florida that not only do they no longer take the excess power you produce, they will charge you for that power, whether or not you use it or they use it. So it's like, why should I put solar in? I'm getting dinged for just having it in the first place. I'm not saving money, it's costing me money. That's the disincentive program. People like to keep things the way they are and the way they were.
Okay. With these last few minutes on this panel, I want to shift gears entirely. I think we're at Anthropocene, we're obviously nuclear enthusiasts, and we think nuclear energy is wicked awesome, and of course, but we shouldn't just reduce it to that. I work on carbon dioxide removal through marine photosynthesis, and that is a form of energy hacking. You're just producing phytoplankton that uses solar energy that you don't have to touch, and then it sinks and it carries carbon dioxide with it. So there are ways of really leveraging much cheaper power that have nothing to do with nuclear energy. When you think about non-nuclear, much cheaper power, what comes to mind? Do you want to start over there?
I mean, I hadn't thought about that, right, there are these sort of free things that we can harvest without intervening, or we can perhaps slightly engineer to make them much more efficient, and then you're really having a positive driver there. To the point of solar becoming radically cheaper, I think there is still a way to go. It's odd in the United States because we have such strong tariffs on solar that they're artificially expensive here, actually. Geothermal, I think we're at the beginning of the reinvention of geothermal energy. There's a long way to go with the technologies we're deploying today, and in a future generation, those could actually be radically cheaper, and that's heat from the ground that exists and gets regenerated, right? So interesting paradigm where it's a resource that can renew itself.
I'm actually very fond of geothermal. Began looking at it years ago and also looking at it on the moon. We have a very strange thing. If you go about 4 or 5 meters deep on the moon, the temperature is constantly about 50 degrees Fahrenheit, despite the fact that during lunar sun time, daytime, it could be 250 degrees Celsius, and it could be the opposite of that in the nighttime. And yet, at a few meters down, it's a constant temperature. Same thing here on Earth. If you go down 4 or 5 meters, you can find out that you've got a constant temperature supply. If you go down deeper, perhaps as much as a quarter mile, but depending on what the strata is, you've got a source of heat. So now you've got both a sink and a source. So this is a really powerful thing. And we now, because of fracking, we really know how to drill holes in the ground that go every which way. So the technology is there, and then it's a question of how do we harness it?
One of the things is that ecosystem services stabilize the chemistry of our planet, also its temperature and humidity. People on islands like Hawaii know what happens if they cut down their forests, why it stops raining, and they've learned not to do that. But we have decimated the life on our planet. There's hardly any mammals left or vertebrates left that aren't humans or are domesticated animals. We need to reverse that quickly, and that means reducing the amount of farmland and killing off all the biofuel crops right away would be my #1 choice. And you look at the currency for UAE, in the middle of the oil empire, they have nuclear power plants on their currency because they don't want to burn oil to process it. That would be stupid. Meanwhile, you've got countries like, palm oil is on the money of other country, which will remain nameless. So we need to. So we can rely a lot more on ecosystem services if we let the oceans return to their previous productivity. That'll require replacing the whale poop that helps the whales keep things stable for us. And these kind of things can happen big scale. And we shouldn't, I'm against prophecy. We shouldn't predict what the Earth's temperature is going to be in the future. We should build a thermostat and decide. And that's not actually going to be difficult. But if nobody tries, or if we're all determined that that would be immoral, it's going to go in some unpleasant direction because it's out of control.
Thank you, Carl. Okay, so with that, I think we're going to thank the panel. Thank you so much. And we're going to move into a fun bit of this.